Jeopardy today. We'll start off with a little warm-up Jeopardy here. Let's see, we got 6.
It's gonna be like all math that we've been working on.
No, it's you'll see. You'll see here in a little bit. Okay. Oops, let me do one thing here.
I said 2. No, but it says like it gives you like a hint. So I think it was a really passive. We solved this.
Okay, so we need a scorekeeper over here. We're gonna do just a little friendly game of Jeopardy. We'll go left half against right half. Andrew, you got the score back there? Okay. So we'll split it right here, so it'll be 6 on 7, right? Yeah, that's about the best we can do. So here's the dividing line right here. Okay. And I'm just going, you buzz in with a raise of the hand. Okay. And if you get it wrong, of course, then I can't remember if you get it wrong, the other team can swoop in and gain credit. And if you get it wrong, we're going to say you lose a point. Okay. So we're just going by ones here. We're not going by just 2 teams. Yep. Okay. So here we go. Here's first question. Okay. Are you ready? Okay. Here's first question. And oh, yeah, whoops. Right here? Fructose it is. Left team's got 1. Everybody get it? What's that? No, you raise your hand. Yeah. Oh, where'd it go? Oh, there it is. Okay.
Oh, they never said what it is.
Yeah, she got it wrong.
Oh. Oh, yeah. Okay. I'm supposed to bring money and I didn't do that. My wife's supposed to give me $6. Can I give it to you on Monday?
Yeah.
Okay, that works.
Or you can just give it to Hunt or Campbell.
What's that?
You can just give it to Hunt as well too.
To who?
Hunt, Mrs. Hunt.
Oh, okay, Ms. Hunt. Okay. I'll just leave it in her box or something. Thank you. Okay, here, yes. Okay, I'm going to give you a pass on that one because I didn't say that. But you do have to. You do have to phrase it in the form of a question. Okay, so what you would say is like, what is fructose? There you go. Okay, but give them a point. Here's the next one. Ready and go. You gotta raise your hand. Okay, so I got a hand raise here, and the answer is geometry, which is wrong. So you lose your point. Who raised their hand? Right here. What is algebra is correct. What is algebra is correct. Yes. Yeah, they can go negative. Yeah, Boolean algebra. Yep. Okay, here we go. Ready and go. What is the manatee? That's 3, isn't it? There we go. Yeah. He's keeping it mathematical. I like that. He's not. We don't. He's keeping it imaginary. He's not keeping it real. All right. Here we go. Okay. You ready? Sorry. I'm sorry about that. That's not good. I'm sorry. Okay. Here we go. Come on now. Yeah, no. Okay. I'll give you a hint. I'll tell you what it starts with. It starts with a G. I'll take either one. No. Lose a point. Okay, I'll give you another letter. Well, I guess I can't do that. Yeah. I can't do that because you guys didn't get that clue. No, I can't. Okay. Time is up. Any guesses? I'm just saying time's up. Yeah. No guesses? Okay. Grendel. Okay. Here we go. Ready? Next one. And go. Correct. Or I'll say either what is or who is. I'll take it. Okay, I'll give it to him. Okay, so they're back to even. They have 0. There you go. Okay. All right, here we go. Next one. Correct. Okay. Here we go. Oh, that was an absolute dead tie. Okay. Okay, we're going leg wrestle for. No, we're going odd or even. Odd or even. It's odd. Okay, I'll take it. Okay. Last one. This is a 3-pointer for the win. You guys are going to have to at least take a guess because they win as of right now.
Let's go. Oh yeah. 2. You gotta get 3. Yo.
Nobody got this one? No guesses? Yeah. Well, it doesn't matter. You're already losing. Love? Nope. Too bad. So sad. Okay. Round 2. They definitely. Okay, so the Thetas definitely won round 1. Here's round 2. Okay, we'll do this one right here first. Right here. Correct. There you go. What is cosine x? Okay. All right. That's an antiderivative. Okay. That's what an antiderivative is, essentially just playing calculus Jeopardy. That's what you're doing. So an antiderivative is reversing the differentiation process, right? It was just an intro to integrals. That's it. Okay, we'll get back to that later. We got to do some calculus. Okay, there'll be a tiebreaker. We'll have some tiebreakers built in.
Okay, well, that's, you guys, for two guesses, they were both wrong, you get double eggs.
Did you have an A in there? Okay, nobody said.
Any guesses on the letter?
Back recording. Okay, so this is an antiderivative. The whole point of this is when you're doing an antiderivative, you're just undoing the derivative process. So if we say, I'm going to rephrase this a little bit. If we say its derivative is f prime of x equals 3x squared, then a correct answer would have been x cubed. Are there other correct answers? Yeah, we could say, for example, x cubed plus 6 would work, wouldn't it? Because the derivative of x cubed plus 6 is 3x squared, right? That could have been f of x, or it could have been x cubed plus 16. So what are we going to do? There's an infinite number of answers here. Yeah, and we're just going to say the all-encompassing correct answer is f of x equals x cubed plus c. Okay, we call this a constant of integration. It has to be there because when we differentiate, we have to account for the possibility there is a constant there, right? Because its derivative would go to 0. C could be 0, but it might be something else. So what about this one then? If the derivative is negative sine x, what should the really correct general solution be? F of x equals cosine x plus c, exactly. Okay, and so, oops, I don't want to do that. And so, really, to write this in a different way, we would call this a differential equation. Okay, why is it a differential equation? A differential equation, you're going to do a lot of work with differential equations over the next several years, I promise you. Differential equations are just equations involving one or more derivatives. That's it, right? So the solutions of differential equations are the original functions that we would have to differentiate to get there, right? So we're working backwards. It's like saying this is the answer. The answer is f prime of x equals 2. Now, what's the question? What's f of x? So what would that one be? 2x plus c, right? Because that's what we would have to differentiate to get that derivative. So we just solved it. You just solved your first differential equation. Okay, let's solve this one. Well, we essentially did it already. X cubed plus c. If f prime of x is 3x squared, then f of x is x cubed plus c. Okay? So that's the process of anti-differentiation. Anti meaning the undoing of, right? So we're undoing differentiation, all right? So graphically, why do we need that c there? Okay, well, here's why. I'm supposed to have a... Is it doing it? Oh, it's doing it on the other screen. Okay. So if we look at... If we look at a graph of the solution, right? We're trying to find all of the functions that have a derivative of 2, just constant 2. Well, isn't that going to be any line with a slope of 2? right? And so we could do something like this. I can say f of x equals 2, but really the solution is y equals f of x plus c, right? And I can make c, if I drag out a bunch of different values of c, what I end up with is what's called a family of curves. Okay, this is the family of curves that represent the general solution of that differential equation. Now, that's not the entire family. If I graph the entire family, the whole xy plane would be blue, right? I just picked some convenient representative examples. I picked the integer values of c. Make sense? Okay. And if I look at this one, it'll be the same kind of picture, right? We want all the functions whose derivative is 3x squared. Okay, well, that's going to be every, I guess I have to do this. So I'm going to make that x cubed. So there's x cubed, right? And by the way, this is kind of cool. In Desmos, you can graph the derivative. So the derivative, hang on here. That's supposed to be 3x squared, sorry. Right, those are all the functions whose derivative is equal to 3x squared. Oh, I did that backwards. Okay, did that backwards. Well, I confused myself. Okay, these are all the functions whose derivative is 3x squared, x cubed plus c, right? I can graph the derivative function here too. I'm going to say g of x, just so you know, this is kind of cool. G of x is equal to f prime. I don't even have to calculate the derivative. It's just equal to f prime of x. And look what it does. It graphs the derivative function. Okay, and there it is. All right, so if I graph the family, then there's the family of all those functions. Let's make this a different color. And they all share the same derivative, which is that now almost invisible purple function that sits back there, right? Okay, everybody get that? It doesn't matter what the vertical offset is. Raising up the function vertically or dropping it down vertically doesn't impact the slope, right? The slopes at every value of x stay the same, okay? Questions? Give me a thumbs on that. How we doing? Okay? I'm just kind of curious if it'll do this. I want to just see if I'm going to define this as f of x equals x cubed plus c and see if it'll still calculate. That's pretty cool. So it'll still calculate that. Even if I have a constant in there, which can have a bunch of different values, it still calculates that derivative function. Oh, maybe it doesn't. Maybe I just broke it. No, it does it. See, it still does it. Still calculates it. Desmos still knows that the derivative is the same for all those. I didn't know if they do that. That's good. Okay. So then let's look at the anatomy of an antiderivative. So there's a different way to describe this too. Antidifferentiation, we say that, we talk about that a little bit, especially when we begin this topic, but eventually we just give up and we call it integration for reasons that we may or may not get to this year. I'm going to try to, but we'll see. An antiderivative then, what we call an antiderivative typically is an indefinite integral. Okay, but both of them are interchangeable. Okay, here's the anatomy of an antiderivative or an indefinite integral. Okay, so this is how we would write it. If we want to figure out what function I differentiate to get something, right? So this is going to be our answer. This is the derivative that we're starting with, right? So this would be, for example, in our previous examples, it would be something like this. We would be saying, if I want to know what the antiderivative of 3x squared is, oh, that's bad color. I'd write it like this. The antiderivative, well, I'd say the integral of 3x squared dx is equal to x cubed plus c. Okay, you get that? So we're playing calculus Jeopardy. Here's the question, there's the answer. That's what we would differentiate to get this. Okay? So we call this part right here, this represents the 3x squared in our example. We call that the integrand. Okay, that's the function we're trying to anti-differentiate, right? This squiggly, really this is just a lowercase sigma, and that's what we call the integral sign, okay? This dx in this case, this is the variable of integration. So this is what the differentiation process would have been with respect to. In this case, we would have had to differentiate with respect to x to get this integrand, okay? On the other side, we've got, this is the antiderivative, the f of x. This is what we'd call the constant of integration. And this whole right side of the equation is what we call the general solution of the differential equation, okay? Do you really need to know all that stuff right now? No, not really. I mean, we'll just talk about it enough that you'll pick up that vocabulary anyway. But I just want you to be familiar with how we would talk about these things, what we mean when we say integral. This is an integral, okay? So there is an inverse nature here, as you've already kind of seen, right? The antiderivative undoes the derivative, but it goes both ways. A derivative undoes an antiderivative also. So we can see then, there's an inverse nature here. If I do an antiderivative of a derivative, I just get back, well, whatever the original function was, right? The antiderivative essentially cancels the prime, right? Flipping that around the other way, if I differentiate an antiderivative, I also get whatever was inside. They just cancel each other, much in the way an inverse functions cancel each other out, right? If f of x and g of x are inverses, then remind me real quick, in order for f of x and g of x to be inverses, what must f of g of x equal? If f of x and g of x are inverses of each other, no? X. F of g of x they would both cancel each other out, and I just end up with x. Okay? But that would have to be true, and g of f of x would have to equal x. That would have to be true for those to be inverse functions. These really aren't functions. These are processes, but they have that same inverse nature. They act sort of like inverse functions. Okay, so now let's make this a little more concrete. So what is the antiderivative or the indefinite integral, whatever you want to say? Let's call it an antiderivative for now. What's the antiderivative of cosine x? I heard negative sine x, but that's not it. It'd be, what would it be? Okay. Sine x plus c, because, how come? The derivative of sine x plus c is cosine x, right? Everybody see that? Okay. We can get a whole bunch of antiderivative rules right away, because it turns out that every derivative rule we have, we could rewrite as an antiderivative rule, right? So for example, because the derivative of kx equals k, we can say that the antiderivative of k dx equals kx plus c, right? Because what happened here? If I differentiate kx plus c, the plus c, I'm not going to write it over here every time, right? Because we wouldn't have written that originally. These will look like the original formulas we had though, right? The derivative of the right side equals k. So that that has to be our new formula. Everybody get that? Okay, we'll pick this up again next time, and I won't put the I tell you what, I'll put the assignment up, but I won't officially start it until next Tuesday.